So in exercise 316, we have vitamin C. And vitamin C is also called ascorbic acid. Now it's acidic because it's going to be giving off some hydrogens into solution. Ascorbic acid has a lot of hydrogens in it. The question is, which hydrogens are the ones it's going to give off first? What are its most acidic hydrogens? And to do that, to determine that without any pKa's or anything for each of the individual hydrogens, we're going to use the qualitative rule of thumb, REO, to assess which hydrogen is most likely to come off. So the first thing you'd want to think about is the atom. That's always the most important factor. We have lots of hydrogens on the molecule. All of the hydrogens are either on oxygens or they're on carbons. Now, oxygen and carbon are in the same row on the periodic table. In the top right, it's sort of carbon, nitrogen, oxygen. They're in the same row. And our rule was that when hydrogens are on two atoms in the same row, the hydrogen on the atom further to the right is more acidic, because that element can stabilize the negative charge that the hydrogen is going to leave behind with its electronegativity. It pulls the negative charge close to the nucleus and helps to stabilize it with the positive charge in the nucleus. So the most acidic hydrogen is definitely going to be one of the hydrogens on the oxygens. It won't be, for example, these hydrogens on that carbon. Okay, so we've narrowed that down. So next, all of those hydrogens tie in terms of an atom. They're all on oxygen, so the atom won't help us determine between those. What we have to do to determine which of those is most acidic is to consider the effect of resonance. The hydrogen that leaves behind the most resonance is going to be the most acidic. Now, if this hydrogen on the far left, if that leaves the molecule and the electrons in that bond become a lone pair with a negative charge, is that negative charge going to be stable or unstable? It's going to be unstable. That negative charge is stuck on that one atom. It's not involved in any resonance. It's 1, 2, 3, 4 atoms away from an atom in a double bond. So there's no resonance here, so that's not our top contender. How about this next one? If that hydrogen goes off into solution as an H+, and leaves the electrons that were in the bond to it as a lone pair on the oxygen with a negative charge, is that a lone pair involved in resonance? No, because it's 1, 2, 3 atoms away from an atom in a double bond, so it's not allylic. It's not involved in resonance. So that's not stabilized. How about this third hydrogen here? If that hydrogen leaves the molecule, the vitamin C molecule, to go off into solution, and the bond that was to it, those electrons end up as a lone pair with a positive charge, is that stabilized by resonance? And it is, because the lone pair is 1 atom away from an atom in a double bond. It's on this oxygen, you go 1 atom over, you're at an atom in a double bond. So that has resonance. How about this next one, this hydrogen at the right? If that leaves the molecule, and the electrons that are in the bond to it, between the oxygen and that hydrogen, turn into a lone pair with a negative charge, is that stabilized by resonance? And that is. It's 1 atom away from an atom in a double bond. So both of these oxygens are stabilized by resonance. So now we've narrowed down the hydrogens even more. We know that the hydrogens are not the hydrogens on the carbon, because that was the atom effector. We know that they're definitely not the hydrogens on these oxygens, because they don't have any resonance. If we were to choose between the hydrogens on those two oxygens, we'd have to see which of those two oxygens has more resonance. Now, let's draw the resonance structures for each of these. So I'm going to just copy this here. So if we take this, oops, let's imagine the resonance for each of these lone pairs. So first, this lone pair on the right, if it's a allylic, so it would go toward the pi bond, and the pi bond would go onto the atom that's away from the allylic lone pair to form a new lone pair. And so the structure you'd end up with would be this one. And this lone pair now is not involved in any resonance structures. Right? It's not allylic, it's not next to a positive charge, so there's no resonance that can have. And so this lone pair is involved in one resonance pattern. So the negative charge will be spread out over 3 atoms in that one pattern. Now let's think about the other lone pair. That's allylic, so it would go toward the atom in the double bond. The electrons in the double bond would go onto the atom away from the allylic lone pair. And so you would end up with this structure. And notice that that structure has another resonance pattern in it. This lone pair is now allylic to this double bond. And so you can get yet another resonance structure where the lone pair goes toward the double bond goes away from the lone pair. And so you would end up with this structure. In other words, this lone pair here is involved in 2 resonance patterns. And so the hydrogen that was on on this oxygen, that hydrogen, that is the most acidic hydrogen in the whole molecule. Because when it leaves the molecule, it leaves behind a lone pair that can get spread out over 1, 2, 3, 4, 5 atoms. Whereas the other hydrogen, this hydrogen over here, when that leaves the molecule, it leaves behind a lone pair that only is involved in one resonance pattern. It spreads the electrons over 3 bonds. The more you spread out charge, the more stable the charge becomes. And so this hydrogen here is the most acidic hydrogen in vitamin C. It pops off the molecule pretty easily because it's on an electronegative atom that's stabilized through resonance, having the charge spread out over 5 atoms. It's acidic enough to bring the pKa pretty low. It's about as acidic as vinegar. And so ascorbic acid is vitamin C because of that hydrogen there.